All right, welcome everybody. Thanks for coming to our workshop on integrating landscape change into ecological workflows using SyncroSim. Hopefully you're in the right place. Just before I start up, maybe I'll introduce myself and the co-leads for the workshop and say a little bit about who we are. So my name is Leonardo Frid. I'm an ecologist with a small company called ApexRMS. Our focus is on ecological forecasting, both software development and providing consulting services around ecological forecasts. And we're kind of a small, just 12-person company, ecologists, data scientists, software developers. Co-leading the workshop with me are Katie Birchard and Carina Firkowski, both also data scientists and ecologists. And the workshop today is about, we scheduled about an hour and 15 minutes. We're hoping to do like our workshop is an hour and then have a little bit of time for questions and discussion. But if you have like short questions, also feel free to interrupt. I think we can keep it fairly informal. It's a hands-off workshop today, so we're mainly speaking to you because of the short timeline. But at the end, we'll provide some resources so you can actually go and download these tools and try them out for yourselves. So here are some of the things we're going to be talking about. Here we go. So just the agenda for today. First of all, what the heck is SyncroSim? And it's not to be confused with sink or swim. Talking about how you can use SyncroSim as a tool for connecting different ecological forecasting models. I'll also talk about what SyncroSim packages are. And then we'll get into some hands-on presentations of how do you interact with SyncroSim, both with a graphical interface, but also using the command line interface in the R and Python packages. We'll get into the details of how would you build your own SyncroSim package if you wanted to. And we'll also do a little bit of a demonstration. For a long time, there's been a desktop version of SyncroSim. We now have a cloud version. So we'll give a little demonstration of also the cloud version of SyncroSim. And then at the end, as I said, we'll give you guys some additional resources so you can try it out for yourselves. So what is SyncroSim? I've been working in ecological modeling for about 20 years, and my colleague Colin, who's the founder of the company, and I, for a long time, we would just develop one-off projects where we would build a model for somebody. And over time, we realized we were often reinventing the wheel. So there's certain things that are very common to ecological modeling. Monte Carlo realization, managing scenario inputs and outputs, understanding the provenance of a suite of model results, being able to track your inputs and outputs, being able to help people visualize the model results. So we said to ourselves, we really shouldn't be reinventing the wheel. We need to create a general framework to help people build ecological models. And this tool should really be agnostic to the model that you're using. And so SyncroSim has been, we've been developing SyncroSim for over 10 years now. And there are hundreds of registered users, and we provide the community version of the software is available for free to academics, governments, and NGOs. For profit companies, we do charge a licensing fee. And part of the reason we can provide it for free is because it's been supported by a number of agencies. There's several of them. The key ones I would say are USGS, the Nature Conservancy, the Government of Canada, and historically the US Forest Service as well. So there's, as I mentioned, we also have a cloud version of SyncroSim. So either of those two websites will take you first to the desktop version, but also to the cloud version of SyncroSim. And that version, as you'll note on the screen capture, is a beta version. So it's fairly new. We're just trying that out, but we kind of see that as a real need for people to be able to use the cloud to collaborate and share models, and also to be able to scale up into using cloud compute resources as well. SyncroSim provides kind of a relational database that will store your model inputs and outputs, and these can be both tabular and spatial. And it's got us this infrastructure to be able to generate these model data pipelines. So being able to connect a series of models together, and we're going to provide 2 examples of that today. One of them is connecting sort of models of landscape change with models of ecosystem carbon and habitat connectivity. And then the other one is connecting models of landscape change with models of species distribution as well. And as I said, you can interact with it via Windows, command line, or R or Python. We have packages as well. The focus has really been on trying to make it scalable to look at large landscapes, many Monte Carlo realizations, to be able to deal with uncertainty. So we have the framework, and then people develop packages against the framework. And a SyncroSim package typically consists of at least 3 different files. So the first of them is a package XML file. You'll see a little bit of a demo of what that looks like, but that really defines your data model. What are your inputs and outputs, and how do you want to structure that input and output data? Then typically there's also some kind of modeling logic. That can be an R script or a Python script. It could also be an existing executable that's wrapped around by a script. So for example, we have packages that make use of the Prometheus fire growth model, which is a C++ executable. So as long as an executable has a command line interface, you could integrate it into SyncroSim. And then there's usually one of the things we've also discovered is it's very hard to share models with people if you don't have the right environment, like in terms of your computing environment. If you have the wrong R packages, the models break. So we also provide a conda YAML file that defines, what are the dependencies of your model in terms of packages. And that automatically gets you all the dependencies. So when the model runs, it runs inside that environment. So this is an example for the Omniscape package, which Carina is going to be showing. The other thing that SyncroSim does is it allows you to connect data to models. So we did some work around the epidemic forecasting COVID-19 here with the BC COVID-19 group. And one real need was getting real-time data that was publicly available through online cloud APIs. So we built some packages that just get the data and get them into your model as well. So a little bit more about model data pipelines and linking models. Today we're going to talk a lot about SDSIM, which is kind of one of the flagship packages for modeling landscape change. And some examples of why you might want to have a data model pipeline. So upstream of modeling landscape change, you might want to have some climate and vegetation data that help you develop like more stand level tree growth models that would help you parameterize your landscape change transitions. When you're running SDSIM, you might want to connect that to a fire behavior model that gives you sort of more realistic, maybe fire perimeters. And then at the end of it, when you've projected landscape change, you might want to see, okay, well, what are the implications for habitat? So connect that with either species distribution models or connectivity models as well. Here's an example, sort of real sort of screen capture for the interface. We have a package called Wisdom. We'll be talking a little bit about later today, and there's a presentation on Thursday on this package. So that package in itself consists of many steps in a model data pipeline, from taking your data and preparing it to be able to run it through your species distribution model, being able to reduce all of your covariates to the key ones that define your species distributions, being able to fit models in maybe different kinds of models, so general linear models, random forest models for species distributions, and then being able to then forecast for a landscape what the potential species distribution might be. So this first example that we're going to talk about is connecting models of landscape change with habitat connectivity. So this is SyncroSim desktop here. And what I'm first showing here are so with SyncroSim on the top left, we have the icon with the cylinder is a library. That's the file on disk that contains all of my model inputs and outputs. And under that, typically we have what's called a project. Usually it's called definitions. So this contains all of your inputs and outputs that are associated with any scenario that you're going to run. It's kind of your global inputs. Typically, these are your lookup tables. What are the land cover classes that I'm working with? And then under that, we have folders that contain scenarios. So that's where you would define specific inputs, like what are my, in this example, I'm going to show 2 scenarios for urbanization, rates of urbanization. And maybe I'll just extend this a little bit. So this window here, a library can have any number of packages associated with it. And so this library, we've got an STSIM package, which is for modeling landscape change. And we've got an Omniscape package, which is for modeling habitat connectivity. And then we've also created a package that helps you connect, sort of take the outputs from the landscape change model, put them into the right format for the habitat connectivity model and be able to connect them. And Katie is going to be able to actually show you the structure of that package and how you could build it with not very many lines of code. So in this example, I'm going to focus on just showing you some of the inputs and outputs for forecasting landscape change and ecosystem carbon. So if I double click on this scenario here, I get a bit of a summary about what this scenario is. This is a scenario for a landscape in Maryland. The reason we chose this landscape is because it's the Julia omniscape.jl tutorial example, if you're familiar with that Omniscape tool. And I'll show you what that landscape looks like in a second. Actually, I think we have a slide for that. Yeah, so that's here. So this is a landscape in Maryland. We've got different NLCD land cover classes. And then in order to be able to model ecosystem carbon, we also incorporate US Forest Service forest type groups as well. And this is the NLCD land cover data set has periodic 30-meter resolution CONUS-wide land cover classes, which we're making use of. In this particular case, this landscape is about 100,000 hectares in size, or 500,000 and 500,000 simulation cells. So it's a fairly small landscape. This is, I think this dot represents the city of Frederick, Maryland. And I'm going to talk, before jumping into the scenarios, I'm just going to talk a little bit more about how STSIM works. So STSIM is this package for forecasting landscape change. It's an open source package, and it uses what's called a state and transition simulation modeling approach. So this approach was initially developed in the early 90s. And the reason I think this approach was, there was a lot of forest landscape change models, but not models that could handle many different types of ecosystems. So both forests and shrublands and grasslands. So it was more general type of approach. The methodology behind this approach, lead author was Colin Daniel, and it's in Methods in Ecology and Evolution, I think a 2016 paper that you see here. So with STSIM, typically you start out with your landscape, and the first thing you want to do is you want to classify it according to different land cover classes. And the land cover classes that you choose are typically driven by two things. What are the questions that you're asking about your landscape? So if you're looking at habitat, typically what are the different classes that a species, how would the species that you're concerned about see the world? And also a little bit about data availability. So I mentioned, NLCD is a land cover data set that we're using for this example as well. And then you can also include ages for each location on your landscape. And you define some kind of a conceptual model that describes, how does one location on my landscape change from one land cover class to another? So this conceptual model includes different kinds of transitions. And these transitions can have either probabilities associated with them, or they can be deterministic with the passage of time. And so we can look at one individual location and see how it's changing as it sort of time passes and transitions occur. And we scale that up to the entire landscape. And often there's uncertainty associated with the transitions. They're probabilistic. So we want to run many Monte Carlo realizations and make projections that include both sort of a mean, but also a range of uncertainty around those projections. A few other features of this approach. So transitions can be set either as probabilities. They can be deterministic with the passage of time. You can also set targets, like if you're looking at something like timber harvest, this is the amount of area that's going to be harvested, or this is the volume, the annual allowable cut for volume target. And they can be stratified spatially or specific to specific state classes. Transition probabilities can also vary with time, and they can be sampled from probability distributions. And you can also include things like external models providing you with sort of mask of where you want transitions to occur. Or you can provide as well some kind of probability distribution around the size of the transition events. So there's kind of a built-in feature for that. And then one other piece which we've added to SDSIM, so this is, so far we've talked about discrete variables, ages and land use, land cover classes, transitions, but people are also interested in tracking things like continuous variables. And so we've added what's called a stock flow add-on to SDSIM that lets you track continuous variables. And the most popular for this is tracking ecosystem carbon. So you have different stocks or pools, and then you have flows or fluxes between pools. You define rates for those fluxes. So those fluxes can either be sort of specific to like a particular forest type and age that might have a specific sort of rate of productivity, so MPP for growth, or different sort of annual rates of mortality and decomposition that are maybe specific to what's already there on the ground. And then they can also be tied through with transition. So when you have a transition occurring on the landscape like a fire, then you can have fluxes associated with that transition. And what this allows you to do is allows you to take this non-spatial sort of stock flow model and apply it spatially, as each cell has essentially its own stock flow model. So you can track how much of each stock is in each pool and how much fluxes are happening at the individual cell level. So now coming back to this demonstration study area in SyncroSim here. So we have a couple of scenarios for this landscape in Maryland that's the same landscape as the JL example. I'll just share a couple of the inputs associated with the scenario. So one input that we typically develop is called the transition pathways. So this shows you both your land cover classes. And in this case, there's quite a few of them because these are the forest types. And then there's a lot of transitions. This is kind of a visual representation of that, but we have a data table that sort of lists all of the different, the starting class, the destination class, the type of transition. So this is a whole list of urbanization transitions that are possible for this landscape, for example. We also have the stock flow model has a similar pathway diagram. So these are our flow pathway transitions where we define our different ecosystem stocks and fluxes for them as well. So those are a couple of the input data sheets, what we call data sheets. And I'm just going to jump to a couple of outputs. So for this particular landscape in Maryland, we included two scenarios, kind of the historical urbanization rates based on the NACCB data, and we actually added a counterfactual scenario where we said, what if urbanization had been happening at a higher rate? So here we have 4 charts. Each of them represents a different land cover change transition. And then the different colors represent different scenarios. We're modeling from, I think the model actually starts in 2009 going to 2021 over a historic time period. And the historical scenario is the red one. And then the counterfactual one, we've really increased the amount of urbanization that is happening in this scenario. So those are the transitions. Let's take a look at a map of land cover classes. So here is our map. And so we've got, again, each column in this case represents a scenario. So on the left, we've got the increased urbanization scenario. On the right, we've got the historical urbanization scenario. They're both identical for time step 2001. Time step 2021, you can see the increase. We can zoom in and maybe find a couple of locations where the increased urbanization scenario might differ from the other scenario. Let me just scroll up here. It's struggling a bit, but you can see this is you can see this area here, for example, has seen a lot more under urbanization under the counterfactual scenario rather than the base scenario. We can also look at maps of ecosystem carbon. So this is total ecosystem carbon. Again, the scenarios are structured in the same way. So top row is 2001, bottom row is 2021. And the scenario on the left is the increased urbanization scenario. And we can get graphical summaries of those scenarios as well. So in terms of changes in ecosystem carbon, so in this case, we're showing the top panel, total ecosystem carbon, and you can see there's some uncertainty across. In this case, we just ran, I think, 10 Monte Carlo realizations. So typically we would do many more. But you can see the range of uncertainty in ecosystem carbon. The center one is net biome productivity, so incorporating both growth and decomposition, but also the effects of land use, land cover change transitions. And then the bottom one is the net ecosystem productivity, so growth and decomposition before the effects of land use and land cover change transitions. So I think I'm going to hand it over to Carina now, and she's going to get a little bit more into the details of how we bring in connectivity to this same model.
Hi everyone. Okay, so Leo just walked you through SDSIM, so the model to, or package to model landscape change. And now I'm going to talk about how you can take an output from SDSIM and link it into a connectivity analysis. So often when we're doing connectivity analysis, we're looking at the current state of the landscape, but it's also helpful to understand how different scenarios of land change or even climate change will affect connectivity in the future. So this kind of pipeline allows us to do that. Okay, so for people who are new to the concept of connectivity, the IUCN defines connectivity as the free movement of species and the flow of natural processes that sustain life on Earth. We can think of things like a connected landscape as essential to supply basic needs such as foraging and reproduction, all the way to supporting species range shifts in response to climate change. So pretty essential component of ecology and ecosystems. And one way to measure ecological connectivity is through omniscape. So omniscape is based on circuit theory. Not to get into the weeds of it, but it models connectivity as an electric current. So you can imagine the species is the electric current traveling through a circuit board, which is your landscape. So it depends on a few components. The first component is the configuration of the landscape or this land cover map. So this is the main output from SDSIM that we're interested in order to run a connectivity analysis. The second component is the species habitat preference. So what are the sources? What are the habitats for that species? In the case of this example, this is a forest-dependent species. So all the pixels in green would be habitat for that species. And then the species movement behavior. So what are the land cover types that it prefers to move through and avoids when moving, and also how far it can move as it moves from a habitat patch through the landscape. And then omniscape outputs this continuous result representing potential for movement flow through the landscape from a low probability of movement in dark purple all the way to the bright colored areas representing high probability of movement. So just really quickly, omniscape treats the electric current as the species that is moving through the landscape. The landscape is your circuit board. And then there are two inputs that represent the landscape. So the first one is the sources layer that represent the species suitable habitat from which it's moving and to which is moving, and the resistance surface, which is this resistance of this surface of resistance to movement, representing how easily it is for the species to move through that landscape. And then the final input is the radius of the moving window, which simply represents the species' dispersal ability. So omniscape then calculates how much current can travel from a source pixel to all the other pixels within that moving window. And it does that in an iterative way by moving the moving window around, calculating current until the entire landscape has been measured. And a common way to summarize this continuous output is to post-process that result into the discrete version of it based on some categories of connectivity. So like a quick overview of omniscape, simplifying a little bit. So you're here, you have run SDSIM, you have a land cover map projection, and you want to calculate connectivity. It depends on a resistance layer, a source layer, and the radius of moving window. So how do you connect that land cover map to the inputs required for omniscape? And this is where that connector package that Leonardo mentioned comes in. So before I switch back to SyncroSim, just want to highlight a few details of this example. So again, the example is based off of the example that Omniscape Julia provides, and we wrapped Omniscape within SyncroSim, but it's calling this executable or the package in Julia. And this example is taking a land cover map and it's reclassifying it into a resistance layer based on a crosswalk table. And I'll show you the crosswalk table in a little bit more detail in SyncroSim in a few moments. Then also based on the list land cover map, it produces the source layer, which in this case, all of the pixels that are forest will become sources for the species. And then it takes those two inputs along with the radius of moving window and it calculates connectivity. So in the code snippets that you just saw are just the code written in Julia, but you don't have to worry about that because we're running with SyncroSim. Okay, so I'm just gonna sit for this bit and switch it over to SyncroSim. Okay, let me just organize the screen here for a bit. How's the volume of my voice? Louder? Yeah, okay. Thank you for the feedback. Okay, so I'll just come back to this packages data sheet. So here's the SDSIM connector package, the Omniscape connector package, but this is also where you could go to add another package to the pipeline if you also want to run a species distribution modeling, or if you want to do something with the connectivity output, you can add other packages over here. Or if you're building your own library from scratch, this datasheet will be empty, so you need to add your packages that you're interested over here. Just close this and pick it up from where Leonardo left. So here we have these two scenarios added to the results so we can visualize the outputs. And I'm going to go back to the land use land cover results. Move it over here, a little bit bigger, and zooming out of the map. So for the Omniscape analysis, we're just interested in the final time step. So we'll be taking these two outputs over here and feeding that into an Omniscape analysis. So for the 2021 time step and for the two scenarios. So this will be our main input that we'll be working with for the Omniscape analysis. So I'm going to close this window. And then let's look at the connector scenarios. So for each scenario, the historical connects to this one, and then the increased scenario connects to this one. So the connector scenario is very simple at this point, and it has two main components. So the first component would be, a slightly older version, but let's just focus on the pipeline datasheet. So the pipeline datasheet tells SyncroSim what scripts to run. So the connector package only has one script, which is in here called prepare SDSIM output for Omniscape. So when you're setting up this connector scenario, all you have to do is select this particular transformer or particular stage of the pipeline. So this is the first bit that you need, pretty simple. As we continue to develop this connector package, though, there will be some extra inputs that you could parameterize, but for now, that's all you need to do. And then the second component is you need to tell the scenario where to get the outputs from SDSIM, and that is done through a dependency. So if you look over here, this scenario 107 SDSIM increased urbanization is the scenario above here. So you're just saying to run the scenario, go look at this set SDSIM output scenario, and that's where you'll get the results from. So that's all the connector package is doing, and Katie will show the code behind that in a little bit more detail after I'm done. So I'll lower this, close these two nodes. The same idea for the historical, it has a dependency on the scenario 106, which links to this scenario. Okay, so I'm gonna now remove this from the results, and I'll close this node. And once you run these two scenarios, the connector scenarios, you're also ready to create your Omniscape run. So for the omniscape run, it will work in a similar way, that it has a dependency on that connector package. So now it knows where to look for that input parameter. If we set a dependency on the SDSIM scenario, it wouldn't know where to get the results that it needs. And since the connector scenario is taking the output and it's saving in a specific place that allows for Omniscape to know where it is, the correct format, that's how this pipeline process works. So let me show you what that means. So if I open this scenario, double clicking on it, just move it to the side. It's a little bit easier to see. So under pipeline, now we have the two stages associated with the Omniscape package. So the first stage is simply run Omniscape. It's your typical Omniscape analysis. And then the second step is to post-process the continuous output that I showed you into the slides into the discrete categories. And this step in particular is unique to the Omniscape package within SyncroSim. If you're running Omniscape outside of SyncroSim, you would need to code that step yourself. Okay, so in terms of inputs, this is the key. This is what the connector package is doing. It's taking the state class map for iteration 1 in time step 2021, and it's saving that output in this data sheet. So it's just saving in the correct place that Omniscape needs to run the analysis. And why is it iteration 1 time step 2021? Because this is in development. So we hard-coded into the script the iteration and the time step, but as we continue to build, this would be a user-defined parameter. You could select exactly which time step you want, if you want one iteration, if you want to look at the uncertainty around connectivity. So that's the first input. The second input is the radius of the moving window, which is here defined as 100 pixels. And then two more things that I want to bring your attention to is under reclassification options. So if you remember, the output from SDSIM is a land cover map, but Omniscape wants a resistance layer. So here we'll have to tell Omniscape how to reclassify that land cover map into the resistance layer. That's why reclassify resistance is set to yes. Then how it should do that. Here is the crosswalk table. For each land cover class that appears in the SDSIM land cover map, what is the resistance value that that land cover map should become? Where are these numbers coming from? Okay, so these numbers are important. They need to link back to the SDSIM map. In SyncroSim and SDSIM, these land cover classes IDs, they're defined at the project scope. So this is the definitions. So if you double click here, just moving it to the side to make a little space. And then if we go to the STSIM tab under states and state classes, here is a list of all the state classes that occur in the data set that we have. But in our particular study area, not all of these state classes occur. This is why the list here is much smaller. Let's bring attention to first the forest classes. So the species is forest dependent. So all of the forest pixels and forest classes will have a low resistance. And what is forest here? Forest is, for example, the ID of 100. So forest, white, red, jack pine has an ID of 100. And this maps over here to ID 100, resistance 1. Same thing for forest class 400, 500, and so on. So if you look over here, the class 400 is also forest, oak pine group. So that's the lowest resistance to movement, ideal land cover class to move from. And then if we take a look at the highest range, highest resistance value of a value of 1000, that corresponds to the state class ID 22. So if we go over here, you can see that that is a developed area of low intensity. So this urban area of low intensity provides the highest resistance value for the species to move through. And then if you notice here, this negative 9999 value for classes 23 and 24, these correspond to medium and high intensity developed areas. So through like the deep urban center, there's absolutely no movement. So in SyncroSim, you define the NA value for that class as -9999. This is your resistance crosswalk table. And then the last option I'll just mention is under general options. Let me just close this, which is likewise, we provided a land cover map, but we also need a source raster. So here you're saying calculate the source from resistance so that all pixels that have a resistance of 1 will become sources. So now we walked from land cover to resistance and source layers. And those are the inputs that you need to run Omniscape. And these inputs are basically defined by these other data sheets that I just showed you. We just inputted them independently into the scenarios. So now you parameterize your 2 scenarios. They're ready to run. We already did that. So let's look at some outputs. So first output is the normalized current. So this is the continuous, I didn't load any results. So let me add this and this one so we can visualize them. So now it should work. So yeah, these are the continuous measures of connectivity under the historical urbanization and increased urbanization. Just gonna zoom in into a few areas of interest and pan across the map. So you can see here that under historical urbanization, this area had some current moving through, and with increased urbanization, it became very, very low current in this area. Let me just zoom out. I'm also interested in this little pocket down here. So zoom and move over there. You can see that there was very high current in this area, and with urbanization, it basically became no data or very low current moving through this area. These maps are really pretty, I find, but sometimes they're hard to interpret because there's no, it's hard to, the relationship between the values is sometimes hard to interpret in terms of their magnitude of the difference. So the discrete version of that are the connectivity categories maps, which you see over here, basically based on some threshold values that you also input at the level of the project. So you define what are your classes, and then for that particular scenario, you define over here, where is it? Here. Category thresholds for each of the connectivity categories, to what thresholds they should reclassify the normalized current into. And you can run some sensitivity analysis on that. But anyways, getting off topic. Over here is that first area that we zoomed in. Now you can see that this pocket that was almost like green and channelized, so green and red, intensified and channelized, became impeded with urbanization. And the same thing if we zoom into that pocket down in the corner, had that high current actually mapped to the channelized bottleneck areas of current, and with urbanization you can see straight away that it's become areas of impeded movement or even no movement at all. There's also some tabular outputs, but I'm getting too excited about Omniscape. I'm forgetting about connecting models. So with that, I'll come back to the slides just to mention a few next steps. So like I mentioned, provide a way for the user to define which time steps they're interested in. Similar way, allow for uncertainty in the connectivity estimates by integrating the iterations. And then lastly, integrating into this workflow, the Omniscape impact package that we have that allows you to calculate the amount of change in connectivity. So here we were just looking at the final maps for increased urbanization and historical urbanization, but you might be interested in the difference between them. So this package allows to calculate difference. So again, it's like connecting another package into the pipeline through the similar process that I just described. Or you might be interested in comparing different time steps. So you have your 2001 and 2021, how much change has occurred between that. But if you're keen on connectivity and have other ideas or needs, come talk with me after the workshop if you have any ideas of how to continue improving that. With that, hand it off to Katie.
Thank you. Okay, hi everyone. I'm Katie. All right, so basically everything that you can do in the SyncroSim desktop, you can also do from our command line interface. So the screenshot here just shows some examples of commands that you can run from our SyncroSim console, as well as descriptions of what those commands do. However, most people don't interact with the console directly. Most people use either our R package called rSyncroSim or our Python package called PySyncroSim. So it's really useful to develop these model workflows using R and Python because you can not only create your models and run your scenarios using the PySyncroSim and rSyncroSim packages, but you can also add in some steps for pre-processing your inputs and post-processing your outputs using your favorite R or Python packages. So I'm just going to go over an example of an R script that uses rSyncroSim to build an STSim library. And we'll provide this STSim vignette for you after the course as well. So just looking at the outline of this script here, we're going to go through just some general setup steps. We're going to create the SyncroSim library. We're going to add model data to the project and the scenarios within this library. We're going to run those scenarios, and then we're going to view the results. All right, so first we'll just load all of the R packages that we need here, including rSyncroSim. Sorry, I'll move this console up so that you can see what's happening here as well. And then we're going to install the STSim package, the STSim SyncroSim package if we don't already have it installed, using the rSyncroSim add package function. We're just going to set our working folder to the directory of this R script. And then for our second task, we're going to create a SyncroSim library. So we can connect to the SyncroSim console using this session function in rSyncroSim. If you don't include any arguments in the session function, then it just uses the default SyncroSim installation location. Otherwise, you can provide a path. So here we can see in the output of this session object that our path is just to the default location of SyncroSim. So next we'll create our SyncroSim library and we've just called it STSim library. And we've specified that we are using the STSim package to build this library. Then we'll create a project within our SyncroSim library called definitions. And then we will create a scenario within that project called mySpatialScenario. So you can look at the data sheets that are associated with your library using the rSyncroSim datasheet function. So we'll just take a quick look at what that looks like here. So the datasheet list that's provided here tells you the scope of the datasheet, so whether it's library, project, or a scenario. And then it'll tell you the internal name and then the display name, which is whatever it looks like in the user interface. So that's an easy way to relate back to the user interface. So I'm going to open up SyncroSim at this point and just show you what this looks like in the UI now. So one useful thing that you can do is you can open up your library in the SyncroSim user interface at the same time you're working on it in R Python, just to check that your outputs are correct. So I'll just open this one that we've just created, and you can see that this is just an empty STSim library that has the project and scenario that we just created. So we'll go back to R. And so now we're going to add some model data to our library. So first of all, we're going to load this STSim terminology datasheet using the datasheet function in rSyncroSim. So when you load a data sheet from SyncroSim, it loads the data as an R data frame, so you can work with it exactly how you would work with any normal R data frame. We can check what columns are available to modify using the str function. And so here we can see exactly what the columns are and the data types that they take. Some of these columns you might notice are factors, and those correspond to drop-down lists in the user interface. So here we're just going to modify 2 of those columns. So we're going to set the units of our model to hectares, and we're going to set the state label X to forest type. And then we can save that information back to the SyncroSim library using the save datasheet function. So I'm not going to go through every single one of these data sheets. I'm just going to quickly run through all of this. But once this has finished running, I'm going to open up the SyncroSim user interface again, and we can see what's happened. Okay. So I'll just refresh. And so now if we go to our definitions, we've filled out all of our project scope data, so we can see that there's now some values in here. And if we go to our terminology data sheet, again, we can see that the amount units is hectares and the state label X is forest type. And the rest of these values are just default with SyncroSim. Then we'll go back to the R script, and we're going to create some scenarios. So first we're going to create a scenario called no harvest, which is just going to be a scenario that doesn't have any harvest transitions in our model. And again, we can take a look at the data sheets that are available to modify. And then the first data sheet that we're going to add here is a run control data sheet. So this just specifies some parameters of your run, such as like how many iterations you're going to run the model for. So in this case, we're running it for 7 iterations. And then we're also telling it that we're going to run it for 10 time steps and that we're running it spatially. So I'll just add that data sheet as well. And then we're adding some transitions to our model. And then we're going to add some initial conditions, and this data sheet's a little bit different because it uses some external file types. So here we're loading some TIFF files into our data sheet, and to load these external file types, you just specify the path to these. So we can also take a look at what those TIFF files look like in R. So for our stratum, for our model, we aren't doing any stratification, so there's only a single value in this spatial layer. This is our state class raster here, so this is just saying for each cell in our landscape what the different state classes are. So a value of 1 is coniferous, 2 is a mixed forest state class, and then 3 is a deciduous state class. And then we're also specifying the ages of the cells in our model. So yeah, for each of these cells, we've given it an age. So I'll just add this information as well to our library. And then we're going to create a second scenario that's based off of our no harvest scenario. So we want to copy all of the data that we've already input into this other scenario and basically build off of it. So the way that we do that is we use the scenario function from our SyncroSim, and we just specify a source scenario as the scenario that we just created. So this will copy all of that data into a new scenario. And then we're just going to change one of the data tables in the scenario to specify, instead of having 0 hectares per year harvested, we're going to harvest 20 hectares per year. And then we can compare those data sheets from the different scenarios. And so here we can see for our no harvest scenario, the amount of harvest transition that's happening is 0. And for our harvest scenario, the amount of harvest that's happening per year is 20. So again, I'm just going to open up the SyncroSim user interface and we'll refresh that, and we can see that our scenarios have now been added. If I open up one of these scenarios, so this is the no harvest scenario. Again, we can see our target harvest area is 0, whereas for our harvest scenario, our target area for harvest is now 20 hectares. Okay, so we'll go back, and now we're just going to run those scenarios. So we're using the SyncroSim run function to do this, and we provided it with both scenarios, so it'll run at the same time. We've also specified the number of jobs as 7, so this will make use of SyncroSim's multiprocessing functionality, so it'll run 7 cores at once. Okay, so those have now finished running, so we'll just grab the IDs of those scenarios that we just ran. And I'm just going to grab one of the output data tables that shows the amount of state class for each of the coniferous, mixed, and deciduous forest types over time. And I'm just going to do some summarizing so that we're going to grab the average amount of each state class across all of the iterations. And then we'll just create a plot. Oops. So this is our ggplot here. So we can see a comparison between these two scenarios. For our harvest scenario, we can see that the coniferous forest type, initially the amount of coniferous in the landscape plummeted, and then it's steadily been increasing. And for our deciduous, it's kind of had the opposite effect. We've increased the number of, or the amount of deciduous forest in the landscape initially, and then it's been decreasing. And the mixed forest has been pretty consistent. And then under our no harvest scenario, we don't see that dip in the coniferous, and we don't see that spike in the deciduous. So we can also grab the spatial outputs from our scenarios as well using this datasheet spat raster function. And we can give it information such as which time step we'd like to grab the our output raster for. So this is just going to grab the output raster for the state classes at time step 5. And then if I want to plot that in R, I can also do that to see what it looks like at that time step. Okay, so I'm just going to go back to the SyncroSim user interface again and refresh, and now we can see that these scenarios have been run. They have this little green arrow on them. And we can also, what we can do as well here is we can recreate the plots that we created in R in SyncroSim to show that they're the same. So we'll just create a state class plot disaggregated by our forest type. Oops. So here we can see that we are seeing a similar trend with the no harvest and the harvest scenarios. We can create a map here as well of our state classes. So I'll just add that to our map. So it defaults to time step 10. It's also chosen some interesting colors here because we haven't given it a legend. But this also shows just the distribution of the different forest types across the landscape at that time step. All right, so that's a really quick introduction to our SyncroSim. Again, we'll send out that R script at the end of the workshop so you can work through it on your own. As well, if you're interested, you can go to the SyncroSim documentation website at syncrosim.com/r-package, and we have a number of articles there to get you started with SyncroSim, and we also have a more in-depth vignette on creating an STSim library. Okay, so now we'll talk a little bit about how SyncroSim packages work. So Leonardo went over this a little bit earlier, but we'll go a little bit more in depth here, and we'll also show a few examples. So the first component that you have in a SyncroSim package is your package XML. So this basically determines the package infrastructure, like which data sheets come with the package, what model scripts there are, how the charts and the maps are laid out, All of that is determined in this XML file. Second, you have a model script. You can have multiple model scripts, and these can be Python or R scripts that carry out the model analysis. And then third, optionally, you can have a conda YAML file. And this is just a file that contains either R or Python or both packages and their versions. And so if you include a YAML file with your package, when a user goes to install your package, SyncroSim will automatically create this environment and run your model scripts using this environment. So it's really useful because the user, they don't have to go and install Python or R or any of those packages. So this is an example of what a package XML looks like. So this is actually the Omniscape STSIM connector package that Carina was going over earlier. So there's a number of important features in this package XML. So first is the package element. This contains your name, your display name, description, and version. Then we have a section where we're specifying our package dependencies. So here we're saying that the STSIM Omniscape connector needs STSIM version 4 and Omniscape version 2 to run. And then third, we have our transformer section. So this is where we specify the model script that we want to run for this package. And you can have multiple transformers as well in your package XML. This one only has one. But these are specified in your library in the pipelines data sheet. And I can just show that as well. I think Carina went over this a little bit earlier. But if we look at our Omniscape connector scenario here, and we go to pipeline, you can see that we've specified this stage here, this prepare STSIM output for Omniscape. And if we just go back to our presentation, you can see that that's this transformer here. And here you also specify the program name, so either Python or R, your program arguments, so this is just the name of your Python script, your conda environment, and your conda environment version. So if you update any packages or versions in your conda environment, you would just update this version number as well. And then also you specify which data sheets this transformer can use. So here we're specifying the output from STSIM is the input to our connector package, and the input that's required by Omniscape is the output of our connector package. So this is the start of the Omniscape package XML, which is a lot more in depth. But just one thing I wanted to highlight here is that you can also add data sheets to your package XML. So this example here is just showing a data sheet that comes with the Omniscape package called Julia configuration, and it's at the library level, and it has a single column called Julia executable. So if I go back to the SyncroSim user interface, and I open up the library under Omniscape, you can see that this data sheet exists here. So yeah, so that's how you would add your own data sheets or data tables to your package. So next, this is an example of a model script for the STSIM to Omniscape connector package. So this was written in Python. And because it was written in Python, here we're importing the PySyncroSim package. If you had a model script in R, you would import the RSyncroSim package. Here we're just loading the library and the scenario that are currently running. Here we're loading the data sheets that are required by this model script. So as we saw in the transformer, we have the output of STSIM and the input to Omniscape. And then we do some manipulation of those data sheets. So here we're manipulating that STSIM data sheet so that it can become an input to Omniscape. So this is what Carina mentioned about us hard coding, just the iteration as 1 and the time step as 21. And that's the data that we're extracting from STSIM to put into Omniscape. And then finally, we would save that data sheet back to the SyncroSim library. And then finally, this is just an example of what a conda YAML file would look like. So yeah, here you just specify your Python packages and their versions. And with that, I'll pass it back to Leo to finish us off.
Another example that I'm not going to get into depth, but just to kind of give you a bit of a sense of the breadth of the types of connections, we focused a lot on connecting SDSIM to OmniScape. I'm going to talk a little bit about connecting SDSIM to another package called Wisdom, Workbench for Integrated Species Distribution Modeling. I'm not going to get into depth into it a lot, but tomorrow there's a presentation by Catherine Jarnovich from USGS on this specific package, and actually the case study that I'm going to describe just now. And actually, I'm getting ahead of myself here. Where's the page of us? Okay. So I'll just jump back into SyncroSim. So here's another library. This one we call the Bufflegrass demonstration. And this is actually a project we've been working on for several years now with USGS and the National Parks Service in Arizona, in the area around Tucson, Arizona, where there's been bufflegrass. It's a species of African perennial grass that's been introduced. And it's taken the Sonora Desert, an area that typically did not have fire risk because there's not much fuel continuity, and created a high risk of fire. Also has impacts on biodiversity in terms of saguaro cactus and other species that are native to the area. For a long time, we've been modeling how bufflegrass is invading and different strategies on managing bufflegrass invasion using SDSIM. But we're also interested on the potential for the suitability of habitat for bufflegrass changing as the climate is changing. So here we're taking a species distribution model that's looking forward with one of the inputs being climate and how that will affect suitable areas for bufflegrass at Saguaro National Park. So the packages that you see listed here are SDSIM. We also have the key packages are, the other one is Wisdom, and then similar to creating a connector package between SDSIM and OmniScape, we have to create a connector package between SDSIM and Wisdom. A couple of examples of the different pipelines here that we use in this system here. So for example, when we run Wisdom, there's a whole bunch of stages from preparing your field data and your covariate data that's going to help you build your species distribution model, fitting your model and using different model fitting approaches. So again, general linear models, random forest, and so on and so forth. There's a whole kind of quite complex pipeline that's taken through with it just running the Wisdom package. And then when it comes to taking those models that you fit, you want to apply them to a specific landscape with different potential variables. So apply to the current climate, but also projected future climate. One of the key variables here for bufflegrass distribution was winter temperatures, limiting the range of where bufflegrass could possibly establish. So that's what these scenarios we have here on the left. So we have establishment probabilities for bufflegrass, scenarios for different points in time with future climates. And again, I'll just double click on one of these. If we look at the pipeline here, for this one, the stages in the pipeline are to apply the different models that we have for that particular landscape using the climate data for that time step, and then to ensemble the different models. So we've got random forest, GLM, I think boosted regression tree maybe for this example, or maxent for this example. So we typically will ensemble the models, and there's different approaches to ensemble the models. And so let's just take a look at two of these outputs. We've got sort of establishment probability for bufflegrass in 2014, establishment probability in 2034, and I'll just show the maps for these two scenarios. Yeah, work. So the top map shows the establishment probability in 2014. The bottom map shows the establishment probability in 2034. And the main thing that you see in this picture is with increasing winter temperatures, to the right, we see like an elevational gradient. So we see the establishment probability going from very low in the higher elevation areas to sort of moving up the mountainside, for example. So that's kind of the output from that sort of probability ensemble across the different fitting methods for the species distribution models. I'm now going to remove these from the results. And just looking at the output. So again, similarly, we have some connector scenarios, but again, just focusing on the SDSIM scenarios. We ran 4 scenarios. So the scenarios are, so there's two kind of levels of management. One of them we call targeted eradication, which is basically no limits on how much buffalo grass gets treated. The other one is target 10% cover. So any cell that has more than 10% cover gets treated, but cells that have 10% cover or less don't get any treatment. So it's more kind of limited resources. For example, you can't treat everything. We'll focus on the high buffalo grass cover areas. We've also looked, as part of this project, we've looked at other strategies like early detection, like find the smallest patches, because there's also, you need to be able to discover the patches before you can treat them. And then we've got two climate scenarios. So static habitat suitability, it doesn't change, or changing habitat suitability with increasing climate. So I'm just going to add these to the results and just show you a couple of graphical outputs. One of them is just the invaded cover of buffalo grass under the two scenarios. Not looking super optimistic in either case, but the green and the blue line represent the scenario that has basically an unlimited budget, and the purple and the red line has the scenario that has more limitation on treating anything that's only greater than 10% cover. But then you see those two diverging, and so that the lines that are higher within those two groups represent the scenarios with increasing also habitat suitability over time. And then just the other one that I wanted to show, often we have what's called transition attributes. So you can assign like costs, or you can assign values to combinations of states and transitions. So we have treatment costs associated with that. So again, this is kind of tracking costs. And you can see that the scenario that targets eradication, which is kind of the blue and green lines, starts out as being more expensive, but actually you see some benefits by focusing early on all the buffalo grass patches rather than wholly on the patches that have higher cover. There might be some future cost savings in terms of how much money you're spending. And actually, in terms of you saw those scenarios had a significantly more positive impact in terms of reducing the amount of area where buffalo grass was covering. So that's just another demonstration of how it could be useful to connect these two modeling approaches. And then just kind of, so the next thing I just want to talk a lot about, so far we focus mainly on the SyncroSim desktop. And this is kind of the architecture of the desktop software. So we've seen that we've got packages which are available from package server similar to CRAN. We see that we have our software on the desktop, and we've got libraries which contain our SyncroSim inputs and outputs, and we can get packages from the server to be able to run different kinds of models. And then typically somebody interacting with the desktop at the level of the data scientist, but you want to be able to share your models with other people. So we have a server version of SyncroSim which runs on a server on the cloud, and that has what's called a REST API, which allows us to build a browser interface against that. So you can take a model that you've built on the desktop, upload it to the cloud, and people can visualize the model results on the cloud. Eventually, what we're moving towards too is actually being able to put the data on different servers, and being able to actually run these models on the cloud as well through a browser interface. So if you want to, make use of cloud compute resources as well. And so I'll just jump to a little demonstration of the SyncroSim Cloud. Listings. Yeah. So it's just cloud.syncrosim.com. And there's a few example libraries that are already published up there. I'm going to show you can kind of scroll through. So these are public libraries. And here's one that makes use of the Omniscape example that Carina talked about. So we can zoom in and we can look at that same landscape that we saw in SDSIM. We can compare different scenarios for that landscape. So we've got the reference resistance scenario here. How do I get it to, it's too zoomed in. Great. There we go. Yeah, so we could look at different resistance scenarios in this example. We can look at the normalized current flow output as well. So that's one example. There's a number of other examples that you can explore. The other thing is, so these are publicly visible, but if you get an account, you can log in and you can publish libraries that you can only share with specific individuals, so you can keep them private as well if you want to share and collaborate with other people. And again, that's what the share button is here. If I sign in, again, I can download a specific library and then run it on the desktop on my own computer. And again, eventually there'll be the ability to be able to run directly from the cloud as well. I think we're getting near the end of the presentation. So the only other thing I just wanted to share was maybe a couple of other resources. So if you go to apexrms.com and you go to tools, the tools page, there's kind of a number of resources where you can look at all of the packages that we've developed against SyncroSim. So there's a whole bunch of different options. And then another resource that I would point you to would be if you're interested in specifically modeling landscape change, the SDSIM, so docs.sdsim.net. And then if you go to the publications, there's tons of examples. So there's over 50 peer-reviewed publications that have used SDSIM for modeling landscape change. That's not to say that, if you have a different landscape change model that you like if you like Lambus, you could also look at developing your own sort of package for running a different landscape change model using SyncroSim. So you don't have to use SDSIM for modeling landscape change, but it does have a long established history for being able to do it. And then we recently had a user conference. So if you go to synchrosim2023.org, so this was a conference that we had last September. And there's a lot of talks, again, different case studies where you see presentations of work that people have applied SyncroSim packages for looking at real world questions. And let me see, is there anything else here? So now we've talked about the resources. I think finally, just maybe a couple of other talks of interest. I mentioned Catherine's talk. So tomorrow at 2:00 in room 2314 on the wisdom package. Tomorrow, Carina is giving a more detailed presentation on Omniscape at 9 a.m. in room 2504. And then tomorrow afternoon, Andrea Norris from Environment and Climate Change Modeling is presenting some work where she's been collaborating with some indigenous communities in the southern interior of BC, again, forecasting cumulative effects impacts on tree cavity excavators using SDSIM, and then some habitat modeling work there as well. And I think that's, yeah, thank you for joining our workshop.